don't want to I don't want to just repeat what we have done in the lectures. So I think this is questions here. Design the shear reinforcement for 650 by 350 cantilever beam. So you have a cantilever beam that is here. So one cover of the fitment is to be 40 millimeters all side, and concrete compress is 10 given 30. Loading is given UDL load 150 kilonewton per meters. You have given these supports 300 millimeters at A and B, and there is no, this is cantilever part, BC is cantilever part. The shear force diagram is drawn for you. That you have a 343 that is passing from the center of this line. 343 kilonewtons shear force here, 0 shear force somewhere, and then you have 270 and 437 shear force, and you have 0 shear force here. Now the question is, we need to provide the fitments. This beam have a like a tensile reinforcement. You can see 2N24 plus 2N20 tensile reinforcement, and you have a tensile reinforcement here. You don't have any fitments yet, so they are looking for what size of the fitments that you can use, and what would be your the diameter of the fitments. So I think that's the questions there. Let's say further to do, we can make an assumption saying that let's say we can use so here we have we need to make a couple of assumptions, meaning that let's assume N10 fitments. Generally we need the N10 fitments for this kind of one, so we can use N10 fitments, and let's say double leg fitments. Meaning that I can show it to you here. This is the double leg fitments, like leg number 1 and leg number 2. Leg number 1, leg number 2. That is a double leg fitments. Let's assume double leg fitment. Generally, we use double leg fitments. So let's start with the check. You know the check that we want to make it. You remember that check, VU maximum check from the standards. I can show it to you, that check that the concrete would not cross. You remember that's always we need to make this VU max check. VU max check meaning that V start it should be less than VU max. Right? That is the check you're going to always make. That check will tell us concrete will not cross and beam size is adequate. If you make this check, then you will have this cross will not happen, and your beam size is adequate. Now, so for that case, let's take a V star. From here, when I scan the shear force diagrams, I can see it is 437 kilonewtons. So 437 kilonewtons is your V star. Now VU max equal to, you can get it from your close table page number 116, close 8.2.3.3 VU max. I just copy these whole equations. We're not talking about transfer in our course. We don't need to worry about the transfer. We just worry about this first one, that we're going to copy this one. If you can't see it, just open your standards and copy that equations from your standards. So let's copy this one. 0.55 FC dash BV DV cot theta V plus cot alpha V cot alpha V over 1 plus cot square alpha V plus PV. Now let's do the one by one. FC dash is given to us is it's given to us 32 megapascals. 32 megapascals. BV is given to us is here 350 millimeters. 350 millimeters. dV, we need to find that dV. So dV equal to, that is called effective shear depth. I can show you where you can find dV. I think if you go on the standard, clause 8.2.1.9 effective shear depth on page number 150, it says that effective shear depth shall be taken as data of maximum of 0.72D and 0.9D. So maximum of 0.72D or 0.9 small d. Now we know capital D, but we don't know small d. Let's calculate the small d. From here we have a this Rio. I think here you have I think this is cantilever, but you have this part is like not cantilever. This part is cantilever. But if you do opposite, like both sides, small d would be, yeah, I think similar. If you make it 3 bar here or 2 bar here, it could measure small d here for this part. You remember that you have this for this part. This is this. For this part is this, right? Your tensile Rio on top here. Your tensile Rio is at the bottom. So, but I think both case D would be same. So D equal to this is 650 millimeters given in our questions, capital D 650. Take away the Rio that you get 28. So this is let's say fitments. So cover is 40 millimeters given in our questions, and 10 fitments 10 millimeters. Take away 28 divided by 2 millimeters because this Rio is 28. So you get about 586 millimeters, which is 0.586 meters. Now someone might say, okay, we might get a different value for this small d on that other parts because you have 650, take away 40 again, take away 10, and here instead of 28 we have and 24 and 20. Yeah, so probably this is 20 divided by 2. So 650 take away 40 is 610, 600, so about 590. It will not going to make a huge difference. You can see 586 and 590. It will not going to make a huge difference. So I just leave with 586. But of course you can do it both sides. But I think there is not big difference. If you have a big difference, you can do the conservative one. But here we have almost same, so 0.86. So now we can calculate dV using these equations. Let me write it again. dV equal to maximum of 0.72D comma 0.9D equal to maximum of 0.72 650 millimeters depth of your whole cross sections, or 0.9 small d is 586 millimeters. So if you simplify that, you will get maximum of 468 millimeters, or you can get 527 millimeters. In that case, you can get dV equal to 527 millimeters. Now we got dV, dV, theta v. Now theta v is equal to 36 degree. What is theta v? So if you take a beam, you will have a crack. So that crack angle is theta v. In our standard, it is theta v equal to 60 degree. I will show it to you here that in these figures, You can look at this one. So by the way, this is flexural crack. You can see this flexural crack here. This is due to the bending. And to stop this one, we provide these guys. These guys here, I think you can't see, maybe take a red pen. These guys will stop this cracking here. These guys, this one, the bottom one. And now you can see this one as well, crack. This crack, this is a shear crack. So this is your shear crack. Shear crack. Now standard saying that, okay, simplification, it is at 36 degree. This vertical crack are flexural crack. And to stop this one, we provide this one, these fitments. You look at these fitments. You can look at this stirrup or fitments. So these are fitments for the shear. So you have stirrups for the fitments to stop this crack. So I think that is 36 degree. I will show you where it is located in our standard. So theta v equal to 60 degree. Now here, theta v equal to 36 degree. As I mentioned yesterday, we have two methods to estimate the kV and theta v. Now, if you use simplified methods and general methods, there is a quite big difference between the simplified methods and general methods. What happens here in the simplified methods, it gives you the overestimation. But I think that is the simplest methods that you can see. This is only these 4 lines, and you have almost 2 pages of work. Yeah, so here they say that theta v equal to 36 degree, but there is an assumption that your ASV over S greater than ASV over S, then you can take kV equal to 0.15 and theta v equal to 36 degrees. So we make this assumption and we can make the check later. Here, rows 8.2, 0.4, 0.3 on page number 119. You have these assumptions: ASV on S, ASV minimum on S. You can take kV equal to 0.15 and theta v equal to 36 degree. So we make these assumptions saying that ASV over S should be greater than ASV minimum over S. We're going to check later. Now, we're going to make these check later. And in that case, kV equal to 0.15 as well. So we find theta v 36. Alpha v is your angle of the fitments. Angle of the fitments meaning when you provide the fitments, this angle is 90 degrees. So alpha v equal to 90 degrees. Generally, we don't provide these inclined fitments like this. We can't provide these fitments. You have this Rio. We generally, this is expensive. In the special cases only we might come across. In that case, you can use alpha v that make the angles. So theta v is your crack angle. Alpha v is your angle of the fitments or stirrups. So alpha v equal to 90 degree. And PV is your for pre-stress. In these beams we are not using any pre-stress, so PV equal to 0. So I think I'm ready to plug the value. VU maximum equal to 0.55 times by I'm using these equations 32 350 32 megapascals times by 350 millimeters BV, and PV we calculated 586 millimeters. 586 millimeters times by this cot 36. Cot 36. By the way, this cot 90 degree. You can get it as a 1 over 1090, and that would be 0. So that would be 0. Is it plus, right? Plus 0 over 1 plus 0 plus 0. So if you use these calculators, you might take the value of 1 543 716.9 newtons. If I divide by thousands, I would get 154.4 kilonewtons. Right. Now, capacity reduction factors. Capacity reduction factor 5. So 5 equal to, we take it 0.75. I can show you where it is. If you go to the table, table 2 point, I think in here you go. Table 2.2.2. Shear is given in the part E. And if you are using the class N fitments, I think we are using class N fitments. If you're using class R fitments, you can take 0.5 and ASV greater than ASV. We're going to make this check, so we can use the capacity reduction factor 0.75 in this case. So capacity reduction factor is 0.75. Just give me a minute. I'll come back. I need to make this correction here. So now we have a 0.75. And let's work out this the 5 VU max. 5 VU max equal to 0.75 times 1544 kilonewtons. We will get 0.75 times 1544. You get 1158 kilonewtons. All right, so in this case, we can check that 5 VU max, which is 1158 kilonewtons, is greater than V star. How much the V star we found? 437 kilonewtons, which is good. 437 kilonewtons. Let's write, since the concrete will not cross under shear, we can also say that beam size, which is 650 by how much? 650 by 350. 650 by 350 size is adequate for shear, right? So if it is, this check does not comes positive, or positive meaning that does not comes as is required, we might need to go back and increase the concrete compressive strength or increase the beam size. Generally speaking, that we generally don't have a issue. The beam generally pass the shear, because under the bending, generally the beam will design for size. But in special cases only, you might not have this check. But I think in this case we are good. Now let's provide the fitment. So we will going to do the 3 part. So let's say you have this beam and you have the support at A, support at B, and that is C. So let's say you have a region A and region B and region C. We will just divide the whole beam. So let's work out at region A. That our standard saying that I can show it to you. 8.2.3.2. Here you go. Maximum transverse shear force near a support. We says that a distance dv from the face of the support provided. It could be face of the supports or it could be at a distance dv from the face of the supports. It can be either. Let's check it out that we have distance dv from the face of the support. So from this close, I can say that let's say we have a shear force diagrams drawn here. Let's say we have a shear force diagram drawn here, something like this. And we have 343 and we have 437 and we have 270. So it says that your crack will start at a distance dv from the face of the supports. And you can clearly see this in our figures as well, in our experiments. We will conduct this experiment, by the way, in our lab. And you can clearly see that this is a support, by the way. Here we put the supports. This is a support here. And there is a mark here somewhere that is a support here. Now you can clearly see that from these supports, your crack is starting here. Look at this crack start. Crack is not started here, right? Not at the support. So it has some distance dv that the crack will start. Also proven in our experiment, as you can see that. So for that case, we will say that this 343 for these regions V stars, we can reduce it to here. That would be our V star instead of 3. So we need to calculate at a distance dv. So let's say y equal to mx plus c. V star, the slope is I think 150 kilonewton per meters. I believe that is the UDL load, and it's downwards negative slope. So minus 150 kilonewton per meters. Let's say x distance we need to get it, and this intercept is 343 kilonewtons. Right. So we need to calculate at a distance dv. What was the distance dv, by the way? Here. dv was 527 millimeters. So we have a 537. So let's plug the value dv minus 150 kilonewton per meter times by 0.537 meters. Let's put it in the meter. 0.537 meter plus 343 kilonewtons. So you will get you get 262.45 kilonewtons as a shear force. So let me correct it here. I think I need to find this x distance. Let me correct it here. 537. So I think the x distance that we're talking about, we need to consider this one as well. I think 150 millimeter supports. So this x distance that we're talking about, that need to be slightly changed, because x equal to 150 millimeters plus the dv, which is 537 millimeters. So 537 plus 150, you get 687 millimeters. So in that case, we just change it to this one, 0.687 millimeters. So minus 150 times 0.687 plus 343, you get 240 kilonewtons. So we get we get 240 kilonewtons as a V stars. Now we have requirements in the standards somewhere here written. Let me check clause 8.2.3.1. Clause 8.2.3.1, which says that your 5 VU should be greater than your V stars. PV is 0 because we don't have a pre-stress. So this YP, we don't need to worry about this lambda P. So PV equal to 0. So I can write 5 VU greater than or equal to V star from clause 8.2.3.1115. So basically capacity of your beam should be greater than your demand V star. So 5 VU greater than or equal to V star, right? Everything all right? Let me check the students here. Everything all right, well? All going well? Any question? I'm just talking with the yes. Yeah, no, you like to wait by yourself, so you get this strategy. Yeah, but some videos are doing the off. Some things, but I hope it makes sense. It's still follow what time is good. Yeah, if you want, we can use so you okay, right? Yeah, you're working. No problem. So I'm just continue. But you always stop. It's next one. I'll just stop. I hope it's okay. Because I can, because the last week when I got speakers, they all run away. So let me know if it is fine. Raise your hand. I will just stop there and come back here. Thank you. Now here 5 VU. So 5 VU we got 5 VU. So VU equal to VUC plus VUS. Where is given? Oops. Is given here. VUC is equal to VUS or VU. So I can. Yes, everything okay? Okay, so in these equations, I just generally put this VUC plus VUS for math purpose. Let's say do the equal to sign and VU. Capacity factor is 0.75. And this first one is your concrete shear capacity. And the second one is your fitment or stir-up capacity. Fitment or steel shear capacity, right? The things that you're going to provide. And V star, we just calculated 240. So in that case, let's calculate the VUC, concrete compressive capacity, KV, BV, DV, square root FCDS. Now, as you know, we need to make these assumptions. ASV on S is equal to greater than or ASV minimum on S. This is an assumptions. And we're going to check later. For that case, we can take KV equal to 0.15. I can show it to you where it is. I think we are using simplified methods. Simplified methods, clause 8.2.4.3 on page number 119. You have this theta V equal to 30. And we made this assumption. We're going to make this check and KV equal to 0.15. So in that case, VUC 0.15 PV. By the way, this VUC, I did not show you where it is. So here you go, VUC. We need to have a FCDS shall not be greater than 8 megapascals. We're going to make these checks. and I copy these equations onto page number 117 on clause 8.2.4.1 to calculate the concrete contribution to the shear strength VUC. Right? Now, in that case, point 15. KV 0.15 dV 350 millimeters given in our questions. I can show it to you here again. dV is 350 and dV, we calculated dV was here 586 millimeters. dV here 527 millimeters. So dV 527 millimeters, square root FC 32. I think I can show it to you where is 32. Here you go, 32 megapascals. So we can make the check. Check square root 32. If I do square root 32, you get about 6 megapascals. So which is less than 8 megapascals. So we can use these equations. I think I show you this in the standards that we have this condition here that shall not exceed 8. We have 6, so should be okay. So if I simplify that, concrete contributions, you will get about 156,511.01 kilonewtons. Sorry, newtons. Because this is millimeters, this is empirical equations, Newton per millimeter square, which gives me 157 kilonewtons. So that is the concrete shear capacity. The concrete saying that I will take care of 157 kilonewtons. You don't need to, the steel, he says that you don't need to worry about 157 kilonewtons. I will look after the 157 kilonewtons. Now, so how much the steel we're gonna look after? So we have these equations already that we can use. Phi VUC plus VUS equal to V stars. You remember that equations we plotted? So we have a 0.75 given here. Let's say at the support A, VA, okay, at a region A or VA. VUC, we got 157 kilonewtons plus VUS, we need to find. A stars, we got about 240 kilonewtons. You remember that we calculated, right? So 240 kilonewtons. So here we get VUC, VUS equal to 240 kilonewtons over 0.75, take away 157 kilonewtons. So 240 divided by 0.75, take away 157, you get 163 kilonewtons as a capacity of your steel. Now, then you have a shear capacity of fitments. So VUS equal to ASV. I will show you where this equation is. FSY.F times by dV over spacing S and cot theta V. Now that equation is clause 8.2.5.2. Here you go. Page number 120. Clause 8.2.5 transverse reinforcement for shear. For perpendicular shear reinforcement, as I mentioned, we are perpendicular. This is perpendicular reinforcement, right? If I put it here, these are your perpendicular reinforcement. They are not at angle. So that alpha V equal to 90 degree. And if you have an incline shear, we need to use this equation, but we have these values. ASV, area of your fitments, area of the fitments meaning this area of your fitments. FSY dot F, we're going to get the fitments range from the yield strength dV. This is the spacing. Spacing meaning what would be the space from one bar to the next fitment. So from center to center distance, that is the S. So this is your S distance. I'm talking about this distance is your X, starting from here, finishing here. That is your S. That we need to find, by the way. And theta V 36 degree. You remember these assumptions that we make here, that your theta V equal to, and we're going to make these checks for that KV, and theta V equal to 36 degree for simplified methods. So we have all the values except few things. FSY dot F is 500 megapascals because we are using N10 fitments, and I can show it to you in the standards that probably somewhere here on the tables. I think here you go on table 3.2.1 on page number 51. If you have a class N fitments or any class N, like N, you have 500 megapascals class N, ductility class N. So 500 megapascals that we can use. ASV, we have a 10 millimeter diameter, so pi by 4 10 square. You get about 78.5 millimeter square. I just take it 80 millimeter square, rounding it off. And you remember that ASV is not just a one single legged, but ASV would be when you have a fitments and when your crack is try to cross the two legs. So that is your ASV. So you need to multiply by 2. If you have a 3 legs, if you have 4 legs, so you need to check that how many legs that's the crack will going to cross. So you, in our case, it's a 2-legged. So you need to multiply by 2. So your final one would be 160 millimeter square. So we have everything. We put 163 times by 1000 to get it in newtons. ASV, we put 160 millimeter square. We put 500 megapascals, Newton per millimeter square. dV, I think we calculated dV before. I think we used dV many times. 527, I believe. Yep, 527. So dV, 527 millimeters over spacing S times cot 36 degree. Right. So let me use my calculators. So 160 times 500 times 527 divided by 163 divided by 1000 times by 1 divided by 1036. So you got let me put 136 250 times 527 divided by 163 divided by 1000 times by 146. Yeah, so let's I think these examples is better to use the 250 megapascal. That would be good. I think just make a changes. I think we need to make some changes here. Please just keep it R10 fitments. Double-legged, 437 kilonewtons. So let me go through it here. 536 where we make assumptions that R10. Let's make a capacity factors 0.7, please. So if you make a 0.7 here, 0.7, because we just want to live with, it's better to use the R fitments here because otherwise the capacity will going to go high, but still is within the limit, 1080.8 kilonewtons. And you have these 1080.8 kilonewtons. So that's all good. This is all good. This is all good. Here you go. We just make it 0.70 here. Then we use VUC. So in here, if I use 0.70, then here 0.70 as well. So 240 divided by 0.7, take away 157, you get 186 kilonewtons. So that's better now. So here you get VUC 186. So now that would be better. So let's say 160 times by 500 times by 527 divided by 186 divided by 1000 times by 1 divided by 1036. You get still it's high. Spacing is 311.9. Let me check again. 160 times 250 times 527. Let's make this one 250. Divided by 186 divided by 1000 times by 1 divided by 1036. Yeah, that is better. 156 millimeter spacing. That is better. So I think use the R10 fitments with two with two leggeds. That will just reduce our spacing. Otherwise, it will just go very high spacings in that case. So now there are a couple of things that we need to make the checks. First checks that we need to make is ASV on S should be greater than ASV minimum of S, right? You remember that we make this check? You remember that we make this check somewhere here. We told that check would be later. Yep, check. We're going to make this check later. So let's do this. Let's say left hand side is equal to ASV on S, which is 160 millimeters square. We found 160 millimeters square over spacing 156 millimeters. So 160 over 156, you get 1.03. You get 1.03. Right hand side is equal to ASV mean on S equal to, I can show it to you under standards. On the page number 114 on clause 8.2.1.7, you have 0.08 square root FC dash BV on FSY dot F. So 0.08 times FC dash times by BV on FSY dot F. So 0. So we have a 0.08, 0.08 square root 32. BV is 350 over 250 for R fitments. I think we change it to the R fitments. So 32 and 350. Well, you can use N fitments, but I think for this demonstration purpose to make all the check, I think this is well suited for teaching purpose. I think it is better I use R10 fitments. So you have 350 BV. Your BV is 350. and your FC dash is 32 megapascals given in our questions. So in that case, you have 0.08 times by square root 32 times by 350 divided by 250. You get 0.63. So you can see ASV on S, which is 1.03, is greater than ASV minimum on S, which is 0.63. Therefore, KV equal to 0.15 is correct. And theta V equal to 36 degree is also correct. Right? You remember that we make these assumptions. Now there is a couple of checks that we need to make. That's a couple of checks that we need to make. It is this. Okay. First checks that that we need to your first fitments. Your first fitments should be located at 50 millimeter from the support. Right? Where is written? I can show it to you here. Yep, here you go. It's very small for you. So on page number 125, clause 8.3.2.3, your first fitment at each end of the span shall be positioned not more than 50 millimeter from the face of the adjacent support. So first fitments will be located 50 millimeters from the support. Second one, that spacing must be continued at the support, continue the distance D in the direction of decreasing shear. What does it mean and where it's written? So here you go, that the shear reinforcement are not less than the calculated being necessary at any cross section shall be provided for distance D from the cross section in a direction of decreasing shears. What does it mean physically? I can explain you everything. That for this shear force diagrams that you have, right? You have this shear force diagram and like this. Now you have 343 kilonewtons and you have 437 kilonewtons and you have 270 kilonewtons. So the first fitments that you're going to provide, your first fitments that you're going to provide is 50 millimeter from the support. So let me draw up these diagrams as well. This is your beam and this is your supports. So the first fitment that you're going to provide is the 50 millimeter from your supports. That is the clause 8.2.3.2. It is a clause 8.3.2.3, right? They said that's okay. Now, where do we stop? Because you can continue. Let's say we have a spacing of 156. Let's make it 155. As I mentioned, we just want to make it rounding it up. So you have 155. Where are we gonna stop? Because you can continue here, and that is very small shear is located here. So you have 155. So there is a conditions that you need to provide the fitments in the region plus PV. Okay, I will show you where they are located. Where you're gonna stop. So I think there is a one clause that they talk about it. Let me go back and check. I think the spacing. Oh, here you go. Require clause 8.2.1.6 on page number 104, saying that you don't need to provide the reinforcement in this region. So V star, this is 0, by the way. V star is greater than, and Ks, we can take Ks equal to 1, or we can find the Ks value, def D equal to 0. So we can find the Ks value. So let's do this one. V star greater than Ks 5 VUC. So let's say V star greater than Ks 5 VUC. Just close this. Okay. And where is given? Is given here. This is 0. So V star greater than Ks 5 VUC. So Ks we can find because your depth is 650, or we can take Ks because V greater than or equal to 650. So we false here. So we can take Ks equal to 0.5. So V star Ks equal to 0.5. This is 0.7, and VUC. What is the VUC that we calculated? Here you go. We calculated 157. So we calculated 157 kilonewtons. So V star is saying that 0.5 times 0.7 times 157, you get 55 kilonewtons. Right? So it says that you don't need to provide when you have 55 kilonewtons, you don't need to provide the fitments. Do not provide the fitments, because I think not here, because that would be different story. Just I'm talking about here for this region, because V star in this region is greater than VUC, right? So that's capacity. So what happens in this region? The concrete will carry shear, and this is a very small shear zone, small shear design shear zone. Right? So for that case, we don't need to provide fitments. But you remember in the lectures I say that you need to provide the fitments to avoid the buckling of your bars. So for that case, probably we're going to provide the fitments here, which are 300 millimeters apart. Okay. And here we're going to provide these fitments. So let's say we want to find this distance, how far that's going to be. We need to find this distance, right? Because from this face to here, how much it's going to be your distance. So it should be 55. So let me write that equations. V star equal to minus 150 kilonewton per meters. Where is 150 coming from? You remember that you have a UDL load of 150 kilonewton per meters. That UDL load on the beam times by distance we need to find, plus this intercept is 343 kilonewtons. 343 kilonewtons. Yep. 343 kilonewtons. So V star we got 55 kilonewtons. So if I want to calculate the X value from here, we can get it. So 55 take away 343 divided by 150, you get 1.92 meters, is basically 1920 millimeters. So it says that in this region, from this end to this end, you need to provide 1920 millimeters of your fitments, And the spacing would be 150. How much spacing we got it? 155 millimeters. So you need to provide the spacing of 155 millimeters in that zone. So let's say let's find that value. We can find this one as well. This distance, how much this distance is, by taking the CR40. So if I plug the CR40 here, you get minus 150, and that distance, let's say 0 CR distance x0 plus 343. So 343 over 150, you get 2.29 to let me write full 87 meters. So you can have 2287 millimeters. So let me draw it up here. I can draw the full pictures. So you have this beam and you have the support, which is 300 millimeters in this one. And the shear force diagram for this particular region, that is starting from the middle, is this like this. So now here, this distance from here to here is 2287 millimeters. The another one is which one we find x distance? We find 1920. So from here to the provide the fitment is 1920 millimeters. You with me, right? Then we need to provide the 150. We need to take away this 150. So from here to here, we will take away 150. So this distance 1920, take away 150. So you have 1770 millimeters, and this is 150. So how I get 1770 is 1920 take away 150, I get 1770 millimeters. So you can provide the from here to here in that fitment. So the number of fitments that you're going to get it, number of fitments equal to 1770 millimeters over 155 millimeters, right? So 1770 over 150, you get 11.8 fitments. 11.8 means 12 fitments, right? So almost 12 fitments that you can provide in this zone. And I think from here to here, how much millimeters is left? From here to here, how much millimeters? 2287 take away 1920 is 36 millimeters. So should be okay. I think we can provide 12 fitments in this zone. So from here to here, as I mentioned, this is your beam. Let's provide a drawing that your first fitments would be at a distance of 50 millimeters. And from up to this point, you're going to provide 12 fitments at the spacing of 155 of the spacing. And this distance would be considered as a 2287 millimeters, right? So I hope it is understood. So you can say that 12, you don't need to show these 12 fitments because you can't fit it, but 12 fitments at a spacing of 155 millimeters, that will do the job. I think there is one more check that we can make it, because the spacing one, you need to make this check that limiting space. You remember that in the lectures, the limiting space one that we want to make the check is so I think the spacing close spacing. I think shear reinforcement shall be placed longitudinally further apart, maximum of 0.5D and 300. Maximum of 0.5D or 300 millimeters. That's what they talk about. I think I made these checks as well somewhere. Let me check. Sorry, minimum of these two. So minimum of 0.5. I think the D is 650, 300. So 650 times 0.5, you get 325. Minimum of 325 millimeters or 300 millimeters. So your limiting space is 300 millimeters. Our S is 155 millimeters, which is less than your check. Limiting spacing 300. Therefore, it is okay. It is okay means the spacing is okay. The spacing equal to 155 millimeter can be provided in region A. Right. Now the same styles, same procedures, exactly everything same. We're going to repeat the procedures for, because we provide the fitments in here. We provided the fitments in here, where this zone. Now we can work in here, close to the support B, and we can provide the fitments in these directions. Same procedures, exactly the same, nothing so much changed. But let me take you through. Let me take you through the procedures. Let me ask the questions here. The students, 1 hour finished. Is everything okay here? Okay. Yeah, I just want to go there. Yeah, so something like that. So there is no right answer or wrong. You just need to comply with all of that. Yeah, but the first thing yes, the first thing I did. So for practice, you can design the whole thing for 4 Yeah, that's right. It's no problem. So then you design it and you might have a cross spacing everywhere. You might get 65 all the way. Yeah. And thought myself that yeah. 60 everywhere, you are doubling up all the video. That's a lot. Yeah. You see, that's a lot. Not 60 millimeters. It's a lot of you doubling it up. You need only 150 or 155, only approximately 150 millimeters on this region. So you need to have force. So that is on the I'm not sure. Probably the labor force might increase, but if you are talking about the long beams and all, you might need to consider a different to save this one. So what I done that we have this one, take it here, 50 millimeters from the start to the VUC. I think this is also wrong. Particularly we need to provide 300 millimeters. But you can't get you can't have this stage. Because otherwise you will have working in the view. To hold this to this top and bottom part in the place, we put 300 millimeters. You can show that one. But theoretically, of the numbers and all, you don't. There is another for clear purpose, you don't have to provide. You will not have that. Because of this is a very small scale. Very small scale, concrete to look after the seal, but these are guys with bottom. There is another story. For technical reasons, we need to take care of this. So it is no harm that you can add pigment the spacing from that point to the development. Yeah, it's very good. I think in the drawing it's not showing. And you can clearly see that these like 447 is closely provided. This like 340 is spacing. See that now. See whether we have something to feel. That's the reason that we guys can be or find something. Everything. I'm not sure. Makes sense? Yeah. So as you say, it's pitched all the way. It's follow all the compliance. No issue. Yeah. The cost will be. Yeah. And you have a multi-story building and
Yeah.
You need to have a balance between your yeah, and when you put the spacing, you don't need to put 156 or just do the 5 mm increment or 20 mm increment. I'm not sure if it's but it's a rules of thumb. Your business can't get more than 156. It's lower, go up. If you go up, then your design will not, your calculations will not multiply.
Yeah.
You can just go down. If you get 150, if you get 124, you get 150. If you get 126, you can get 125. Any one of the extra will not count. And if you extend distance d, then you stop. And first statement, I hope everything makes sense. Any questions there? I hope it's clear. So I continue over that just to record. Yes. And the students online, and then we go from there. All right. So the next part is to do with this zone. Same story. We calculate the. Let me draw up the beam. Let me draw up. So we have this beam. We have support at A. We have support at B, and this is C. And we have a shear force diagram. Look like this, which is 437 kilonewtons and 270 kilonewtons. And we have 343 kilonewtons. Now, in this case, we can take 437 as a V star B, but the standard saying that you can get away with the distance dV. You remember that the spec will not start at the supports at a distance dV. I show you that in the standards. I can show it to you again. So that distance dV we calculated already. Where is it? I think dV was 527. So we can say that this one would start at 527. So we can just get the V star here instead of 437. And by the way, between these two guys, we can make it maximum. So V equal to minus 150x plus 437 kilonewtons. That is coming from here. And we need to calculate this minus 150. That is kilonewton per meters. Let's write kilonewton per meters. X kilonewton per meters. X is dV. Now the dV was we calculated dV. Here you go, 527. So 0.527. 0.527 meters plus 437 kilonewtons. So minus 150 times 0.527 plus 437. You get 358 kilonewtons V star instead of 437. So we can design it for 358 kilonewtons instead of 437 distance dV. I can show it to you in the close that maximum shear distance dV. Here you go, page number 116, close 8.2.3.2. You can get the I think you can get the you can design it for 437, no problem. But if you have a distance dV from the face of the supports, for these cases, we can have economic designs. If you put 437, you put dV distance. Now we already know VUC. I think we can design. You remember these equations? V star equal to 5 VUC plus VUS. You remember that, right? I can show it to you here again.